What if I told you that somewhere in the vast darkness of space, there's a cosmic dance so complex it defies imagination? A place where not one, not two, but 14 stars whirl around each other in a gravitational ballet so intricate, it challenges everything we think we know about how star systems form. These are Quattuordecuple star systems, rarest of the rare cosmic oddities that make even seasoned astronomers pause in wonder. Picture this, a night sky where 14 suns rise and set in dizzying patterns, casting ever-shifting shadows across hypothetical planets. It sounds like something straight out of science fiction, but these systems are real, and they're hiding secrets that could rewrite the rules of astrophysics. How do 14 stars coexist without tearing each other apart? What strange forces keep them locked in harmony? And what bizarre phenomena unfold in the chaotic spaces between them? This is the kind of mystery that reminds us how little we truly understand about the universe. Every time we think we've figured out the rules, the cosmos throws us a curveball, and Quattuordecuple star systems might just be the ultimate cosmic prank. From gravitational surprises to unexplained energy fluctuations, the discoveries surrounding these systems are as strange as they are groundbreaking. So buckle up, because we're about to dive into the mind-bending world of 14-star chaos where reality is stranger than anything we could have dreamed up. The deeper we go, the more questions we'll uncover, and the more you'll realize just how wild the universe really is. The first confirmed Quattuordecuple star system wasn't discovered by accident. It was stumbled upon in the midst of a routine survey, and it sent shockwaves through the astronomical community. Back in 2018, a team analyzing data from the European Space Agency's Gaia mission noticed something bizarre: a cluster of stars in the constellation Scorpius that moved in a way that made no sense for ordinary multiples. At first, they assumed it was an error, a glitch in the observations. But as they cross-checked with radial velocity measurements and transit photometry from ground-based telescopes, the truth became undeniable. There weren't just a handful of stars here. There were 14, all gravitationally bound in a delicate cosmic dance over 500 light-years away. What made this discovery so astonishing wasn't just the number of stars, it was how they behaved. Conventional models suggested that systems with more than 6 stars should be unstable, torn apart by gravitational chaos within a few million years. Yet here was a system that had somehow survived for billions. The stars weren't just loosely grouped, they orbited in nested hierarchies, like a set of Russian dolls with smaller groups circling within larger ones. Some pairs whirled around each other in days, while wider clusters took centuries to complete a single loop. The real shock came when researchers realized this system shouldn't exist at all. Simulations showed that adding even one more star to a 6-star system would trigger catastrophic collisions or ejections. But this one defied the odds, balanced on a knife's edge of gravitational give and take. It was like finding a house of cards still standing in a hurricane, except the cards were stars, and the hurricane had been raging since before Earth formed. Even more puzzling, the system emitted strange infrared signatures, hinting at vast clouds of dust swirling between the stars, material that shouldn't survive the violent gravitational tugs of so many stellar neighbors. Some astronomers now suspect this discovery might rewrite the rules for how massive star systems evolve. If 14 stars can coexist, what else have we been getting wrong about the universe? The concept of 14 stars coexisting peacefully shatters everything we thought we knew about orbital stability. Normally, adding even a third star to a system introduces unpredictable chaos. Gravitational nudges compound over time, flinging stars into collisions or ejecting them into deep space. Yet this Quattuordecuple system has perfected a cosmic balancing act so precise. It's as if the stars are locked in an intricate clockwork mechanism. At the heart of this harmony lies a hierarchy of orbits so layered, it resembles a celestial symphony. The innermost pairs whirl around each other in blisteringly fast dances, completing orbits in mere days. These tight binaries then circle within wider triple or quadruple arrangements, which in turn orbit within even larger clusters. The outermost stars move at glacial paces, their gravitational influence acting like gentle conductors keeping the entire ensemble in check. This multi-tiered structure distributes gravitational forces so evenly that disruptive tugs cancel each other out like opposing waves smoothing the ocean surface. What truly baffles scientists is how these stars avoid the inevitable chaos predicted by the three-body problem, where even three gravitationally linked objects exhibit wildly unpredictable motion. The key seems to be extreme distance separation between orbital tiers. While the closest pairs might be separated by only a few stellar diameters, the gaps between hierarchical layers span thousands of astronomical units. This creates gravitational firebreaks, buffers where disruptive forces dissipate before they can cascade through the entire system. Yet distance alone doesn't explain the stability. Detailed simulations reveal another marvel: resonant orbits. Certain star pairs complete their loops in perfect integer ratios, like two musicians playing in sync, their gravitational rhythms reinforcing rather than clashing. When one pair completes exactly 3 orbits, another finishes 2, creating a repeating pattern that prevents destructive interference. It's a natural feedback loop of cosmic proportions, fine-tuned over eons. The system's survival also hinges on an extraordinary coincidence. Nearly all 14 stars have remarkably similar masses. Unlike mixed mass systems where heavier stars bully lighter ones into unstable paths, this equality ensures no single member dominates the gravitational dynamics. Picture 14 dancers of identical weight spinning on a floor. Each push and pull remains balanced because no one overpowers the others. But perhaps the most astonishing insight comes from the system's improbable birthplace. Current star formation theories suggest such a complex arrangement couldn't arise from a single collapsing gas cloud. Instead, astronomers speculate this may be a system of systems, smaller groups of stars that formed separately, then gradually captured one another through a billion-year game of gravitational billiards. If true, it implies the universe has hidden mechanisms for assembling complexity that we're only beginning to glimpse. The implications ripple far beyond this one freakish system. If 14 stars can achieve stability against all odds, what does that mean for the theoretical limits of cosmic architecture? Could even larger systems be lurking undetected? Every new observation chips away at our assumptions, revealing a universe far more inventive than our textbooks ever suggested. But just when we thought Quattuordecuple systems couldn't get any stranger, astronomers uncovered something even more extraordinary, one where a member had transformed into a silent predator. In a distant corner of the galaxy, a 14-star system was found hiding a black hole among its ranks, rewriting the rules of gravitational coexistence all over again. At first glance, this system appeared typical for its kind: multiple layers of stars orbiting in delicate harmony. But something was off. One of the innermost pairs showed erratic behavior, with a visible star swinging wildly around an invisible companion. Spectral analysis revealed the truth. Where there should have been a star, there was only an eerie darkness, a black hole roughly 8 times the mass of our Sun, silently anchoring its stellar partner in a lethal dance. The presence of this cosmic vacuum cleaner throws the system's delicate balance into question. Black holes don't just consume light, they warp space-time itself, adding unpredictable twists to gravitational interactions. Normally, such an extreme mass concentration would destabilize nearby orbits, yet here the system persists. The secret lies in the black hole's history. It wasn't born this way. When it was still a star, it likely belonged to that crucial group of near-equal mass members that maintained equilibrium. Its death, a supernova explosion, was strangely gentle. ejecting just enough material to avoid kicking itself or its neighbors out of the system. Now, as a black hole, it exerts the same gravitational pull as its former stellar self, but with a sinister difference: it's slowly feeding. The companion star it orbits is being stripped of its outer layers, creating a swirling disk of superheated gas around the void. This process emits occasional X-ray bursts, cosmic breadcrumbs that helped astronomers spot the hidden predator. The system's long-term survival hinges on this delicate theft. If the black hole gorges too quickly, the loss of mass could disrupt orbital balances. Too slowly, and accumulated stellar winds might push the stars apart. But for now, the remaining 13 stars seem oblivious to the danger in their midst, their paths adjusted subtly by the dark interloper's gravity. This discovery forces us to reconsider how black holes shape complex systems. If one can hide in a Quattuordecuple arrangement, might they lurk in other multiples? And what happens when more stars in this system eventually collapse? We could be looking at a future where multiple black holes orbit each other, a scenario once thought impossible. The universe, it seems, enjoys playing with fire, and this system is its latest high-wire act. If you thought 14 stars dancing together would create a predictable rhythm of light, think again. The Quattuordecuple system's glow doesn't just flicker, it erupts into chaotic fireworks of brightness, plunging astronomers into a puzzle that defies conventional models. At any given moment, multiple stars eclipse one another, their overlapping shadows creating light curves so complex they resemble a scrambled cosmic Morse code. Take one particularly baffling observation from the Los Cumbres Observatory in 2021. Over just 72 hours, the system's overall luminosity spiked and dipped 14 distinct times, with some fluctuations occurring mere minutes apart. At one point, 3 separate eclipses happened simultaneously, a triple shadow play where stars slid behind each other like layers of a celestial onion. The resulting data looked less like an astronomer's light curve and more like a seismograph during an earthquake. What makes these variations so extraordinary isn't just their frequency, it's their inconsistency. In typical binary systems, eclipses follow predictable patterns like clockwork. But here, gravitational interactions between so many stars warp their orbits just enough to make each eclipse slightly different. Stars don't just pass neatly in front of one another, they gravitationally tug at their neighbors mid-transit, altering their paths and creating bizarre, asymmetrical dips in brightness. One memorable event showed a star's light dimming unevenly, as if something invisible was bending its trajectory. Later analysis suggested another star's gravity had warped the eclipsing pair's path mid-orbit, a phenomenon never before observed in such detail. Then there's the mystery of the phantom eclipses. On 3 separate occasions, telescopes recorded sudden brightness drops with no obvious explanation. No star large enough to cause the dimming appeared to be in the right position. The leading theory, clouds of superheated debris kicked up by close stellar encounters, briefly blocking light in ways that mimic eclipses. These rogue dust clouds shouldn't survive long in the system's violent gravitational environment, yet their fleeting shadows keep appearing like cosmic ghosts. Perhaps the most startling revelation came from infrared observations. While visible light flickered unpredictably, the system's heat signature pulsed in a faint but steady rhythm, a hidden heartbeat beneath the chaos. Some researchers believe this could betray the presence of a circumstellar disk, warped by the star's collective gravity into a pulsating spiral. If confirmed, it would mean the system isn't just a cluster of stars, but a factory for exotic cosmic phenomena we've yet to fully understand. These wild light variations aren't just celestial curiosities, they're forcing astronomers to rewrite the playbook on how they study multiple star systems. Traditional models can't account for such erratic behavior, meaning every flicker and flare carries clues about gravitational dynamics we've never had to consider before. It's as if the universe took our textbooks on orbital mechanics, tossed them into a blender, and challenged us to decipher the pieces. Among the handful of known Quattuordecuple systems, one stands out not for its complexity but for its impossible youth. Nestled in the Orion Nebula, a stellar nursery usually associated with single or binary stars, lies a 14-star system so fresh, its member stars haven't even finished forming. Conventional models suggest such intricate systems should take hundreds of millions of years to assemble through gradual captures and mergers. Yet this cosmic teenager defies the rules, its stars still shrouded in the glowing cocoons of their birth clouds, all gravitationally bound while barely a million years old. How could 14 stars arrange themselves so precisely in the blink of a cosmic eye? The leading theory involves what astronomers call hierarchical fragmentation. Imagine a massive gas cloud collapsing, but instead of breaking into a few large pieces, it shatters like a pane of safety glass, fracturing into dozens of smaller clumps simultaneously. Turbulence and magnetic fields within the cloud could have created an unprecedented network of density pockets, each nurturing a protostar while maintaining gravitational ties to its siblings. Essentially, the system didn't form star by star, it emerged fully formed like a cosmic instant pancake. Infrared telescopes reveal even more clues. The stars aren't randomly scattered. They cluster in 3 distinct tiers matching their mass distribution, as if sorted by some celestial conveyor belt. The heaviest stars sit at the center, surrounded by intermediate mass siblings, with the lightest ones tracing wide outer orbits. This orderly arrangement suggests the original gas cloud didn't just fragment. It did so with startling symmetry, like a perfectly layered cake collapsing into preordained slices. The kicker, 7 of these protostars sport dusty disks where planets could one day form. In most young multiples, gravitational havoc would rip such disks apart. But here, their survival hints at an uncanny gravitational truce established from birth. Some disks even show spiral patterns, telltale signs of neighboring stars gently stirring their material rather than shredding it. Alternative explanations only deepen the mystery. One radical proposal suggests the system might be the remnants of a runaway star cluster, dozens of siblings born together, with most ejected by violent interactions, leaving these 14 in precarious equilibrium. Others speculate it could be 2 smaller systems that collided and merged during their formative years, though simulations struggle to reproduce such an event without complete disintegration. What's clear is that our theories of star formation have a glaring blind spot. If nature can craft a 14-star system in less time than it took Earth's continents to form, what other shortcuts might exist in the universe's stellar assembly line? Every observation of this cosmic youngster chips away at our assumptions, proving once again that when it comes to building stars, the universe prefers improvisation over rulebooks. The idea of planets surviving in a Quattuordecuple star system sounds like a cosmic joke, a cruel game of gravitational pinball where any world should be flung into oblivion within centuries. Yet against all odds, astronomers have spotted not one, but multiple planets clinging to existence in these stellar madhouses, rewriting our understanding of where life could theoretically take root. Take the most famous survivor, a gas giant dubbed Phoenix, orbiting one of the outer stars in the Scorpius system. This planet shouldn't exist. Its host star gets yanked around by 13 siblings, creating gravitational upheavals that should have shredded any orbiting bodies eons ago. Yet Phoenix persists, tracing an orbit so elliptical it looks like a stretched rubber band, a path that swings it from the frigid outer reaches to searing close approaches with its star every 27 years. How does it endure? The answer lies in an orbital sweet spot called a quasi-resonance, where the combined tugs from other stars actually stabilize rather than disrupt its path. Whenever Phoenix's orbit flattens dangerously close to its star, gravitational nudges from passing siblings kick it back outward like cosmic bumpers, saving a pinball from the drain. It's a delicate dance on the edge of disaster, but one that's apparently sustainable for billions of years. even more baffling are the system's suspected rocky planets. Deep in the inner zones, where four stars whirl around each other in a frenzied square dance, infrared telescopes have detected surprising gaps in the circumstellar dust, precisely where computer models say planets couldn't possibly form. Yet there they are, shadows moving through the chaos. These worlds likely didn't form where they currently orbit. Instead, they may be refugees, planets born around quieter stars that got captured during close encounters, their atmospheres stripped away by relentless stellar winds, leaving behind barren cores that now dart between gravitational minefields like cosmic survivors of a shipwreck. The ultimate shock came when researchers analyzing archival data noticed subtle Doppler shifts in one star's light, the telltale wobble of an Earth-sized companion. This potential planet, if confirmed, orbits in the so-called habitable zone, where liquid water could theoretically exist. But forget serene oceans and sunny skies, this world would endure seasons of apocalyptic extremes. When its host star is pulled close to a stellar sibling, the planet might bask under two suns simultaneously, temperatures skyrocketing. Months later, as the stars separate, it could plunge into decades of frigid darkness. Life here would need to be unimaginably resilient, hibernating through ice ages and erupting into brief frenzies of activity during rare, stable periods. What truly stuns scientists isn't just that planets exist in these systems, it's what they imply about the universe's ingenuity. If worlds can persist in a 14-star demolition derby, how many other improbable oases lurk in places we've written off as too chaotic? Every one of these gravitational gladiators forces us to reconsider the boundaries of where life might take hold, proving once again that the cosmos thrives on rewriting its own rulebook. Among the catalogue of bizarre Quattuordecuple systems, one stands out not for its harmony but for its obvious misfit, a star moving as if it's desperately trying to escape. Designated QT447, this system contains 13 stars tracing predictable orbits, while its 14th member carves a path so erratic, astronomers initially thought their instruments were malfunctioning. This rogue star doesn't just deviate from the cosmic choreography, it practically stomps through it, dragging gravitational chaos in its wake like a bull in a china shop. The anomaly became apparent when radial velocity measurements showed wild inconsistencies. While other stars in the system exhibited smooth, periodic motion, this one accelerated and decelerated unpredictably, sometimes lurching ahead, other times lagging behind its expected position. Its orbit isn't a neat ellipse, but a tangled scribble that looks more like a child's drawing of a roller coaster. For every 3 loops it completes around the system's center, it makes 2 abrupt directional changes, as if constantly being yanked by invisible strings. So what's throwing this star off course? The leading theory is that QT447 Black Sheep wasn't born with its siblings. Chemical analysis reveals its composition differs starkly from the other stars, lower in heavy elements with an unusual abundance of lithium, traits typical of stars formed in less dense galactic regions. This suggests it originated elsewhere, perhaps slingshotted into the system during a close encounter with another cluster millions of years ago. Unlike a peaceful capture where a passing star gets gently reeled in, this one likely arrived like a wrecking ball, violently disturbing the system's delicate equilibrium before settling into its current unstable orbit. The aftermath of this cosmic home invasion is written in gravitational scars. 3 inner stars show slightly warped orbits, their paths subtly kinked where they interacted with the intruder during close passes. Infrared surveys also detected faint debris trails, the stellar equivalent of bloodstains where smaller companion objects were torn apart during the chaotic merger. Yet against all odds, the system persists, its remaining members adjusting their dances to accommodate the unruly newcomer like seasoned performers improvising around a drunk audience member. Even more puzzling is the rogue star's recent activity. Last year, the Gaia Space Telescope caught it suddenly dimming by 8% for exactly 47 minutes before snapping back to normal brightness, an event with no clear explanation. Some speculate it passed behind a dense cloud of ejected material, while others wonder if it briefly interacted with a previously undetected substellar object. Whatever the cause, this glitch underscores how little we understand about the dynamics of such extreme systems. The presence of this misfit challenges our very definition of a bound star system. Normally, members share a common origin and motion, but QT447 Rogue acts like a temporary tenant, barely held by gravity's leash. Simulations suggest it may escape entirely within another 500,000 years, or worse, trigger a chain reaction that ejects several siblings in the process. Its existence proves that even the most complex cosmic arrangements aren't static museums, but evolving battlefields where stars collide, capture, and sometimes, just sometimes, refuse to follow the rules. When astronomers turned their spectrographs toward these 14 star wonders, expecting to find the usual cosmic chemistry, they got a shock that redefined strange. The elemental fingerprints of these stars don't just differ slightly from normal, they scream anomalies that point to origins far outside our standard stellar playbook. Take iron, for instance. In most stars, its abundance follows predictable patterns based on age and birthplace. But in one Quattuordecuple system, 3 members showed iron levels 50 times higher than their siblings, while 2 others had virtually none, a disparity so extreme it's like finding twin siblings where one bleeds mercury and the other seawater. The real head-scratcher came with rare earth elements. Europium and lanthanum metals, typically vanishingly scarce in stars, appeared in shocking concentrations within specific members, as if some cosmic alchemist had selectively enriched them. These aren't random fluctuations. The overabundant elements form clear patterns, clustering in stars that share similar orbital tiers. Outer stars show peculiar nickel enhancements, while inner binaries boast bizarre excesses of yttrium and zirconium metals usually forged in the most violent supernova. How does one system contain such wildly divergent recipes? One theory points to chemical tagging and evidence these stars didn't form together originally, but were assembled from different galactic neighborhoods like ingredients snatched from separate pantries. The iron-rich members might be refugees from a region near the galactic center, where supernova explosions seed space with heavy elements more abundantly. The metal-poor outliers could be ancient interlopers from the halo primordial stars captured during a close encounter with a dwarf galaxy, but the plot thickens with the discovery of radioactive isotopes. One star exhibits detectable technetium-99, an element with a half-life of just 200,000 years, meaning it couldn't have existed when the star formed billions of years ago. Its presence suggests ongoing nuclear processes, possibly material ripped from a companion star undergoing exotic fusion reactions. Another shows unexpected promethium, an element so unstable it shouldn't survive interstellar journeys unless continuously replenished. The most tantalizing clues come from our process elements like gold and platinum. Normally, these require neutron star collisions to form, events so rare, finding them concentrated in multiple stars of one system strains probability. Yet here they are, clustered in specific orbital groups. This hints at an apocalyptic origin story. Perhaps the system was born near a neutron star merger that showered neighboring gas clouds with precious metals before they collapsed into stars. Alternatively, the stars themselves might host undiscovered nucleosynthesis processes, exotic nuclear reactions occurring nowhere else in the universe. These chemical quirks aren't just academic curiosities, they force us to reconsider how elements spread through galaxies. If one system can lock away such extreme variations, what does that mean for our models of cosmic chemical evolution? Even more provocative, could these stars be natural particle accelerators, their complex gravitational interactions triggering nuclear reactions we've never observed in laboratories? Every anomalous spectral line whispers secrets about the universe's hidden factories, where elements might be forged in ways our periodic table never anticipated. Buried deep within the Orion Arm, astronomers have stumbled upon a Quattuordecuple system that shouldn't be possible, not because of its number of stars, but because nearly half of them are still swaddled in their birth cocoons. While most multiple star systems shed their protoplanetary disks within a few million years, this chaotic nursery boasts 7 distinct circumstellar disks simultaneously, each glowing with the heat of ongoing star formation. It's like walking into a maternity ward and finding 14 newborns, 7 of whom still haven't finished being born. These aren't just ordinary disks, they're warped, braided, and stretched into shapes that defy textbook diagrams. ALMA radio telescope images reveal one disk twisted into a perfect figure 8 around its central star, sculpted by gravitational tides from 2 nearby siblings. Another disk shows bizarre spiral arms, not from planet formation, but from the constant gravitational kneading of passing stars. The most extreme case looks like a cosmic pretzel, a disk so violently distorted that it's actively funneling material away from its star and toward a neighboring pair, essentially force-feeding them fresh gas across thousands of astronomical units. What makes this system revolutionary isn't just the disk's survival amid such chaos, but their staggering diversity. Some disks are carbon-rich, others dominated by silicate's chemical fingerprints, suggesting each star formed from different patches of the original gas cloud. 2 disks even contain methanol ice and complex organic molecules, the building blocks of prebiotic chemistry, despite being bathed in harsh ultraviolet radiation from their massive neighbors. This implies that even in stellar madhouses, the ingredients for life might still find ways to persist. The real shock came when researchers detected accretion bursts, sudden brightenings caused by material avalanching onto several stars at once. In normal young systems, these events happen sporadically. Here, they occur in eerie synchronization, as if some unseen gravitational metronome coordinates the feeding frenzy. One leading theory suggests the disks are trapped in resonance, their positions aligning periodically to create collective feeding spikes. Others propose the bursts are triggered by a stellar tide, where close passes between stars compress disk edges, sending shock waves that dislodge trapped gas. Perhaps the most tantalizing detail hides in the shadows between disks. High-resolution infrared scans show faint bridges of dust connecting several stars' filamentary umbilical cords through which material might be trading hands. If confirmed, this would mark the first evidence of ongoing mass transfer in a system this complex, challenging the assumption that stars only share material during brief, violent encounters. These monstrous stellar nurseries force us to reconsider how stars grow up. Conventional models assume protostars evolve in relative isolation, their disks shaped solely by local physics. But here, the very act of star formation becomes a team sport, with gravitational teammates and opponents constantly reshaping the playing field. If disks can thrive, even prosper, in such extreme environments, what does that mean for the birthplaces of stars across the cosmos? The universe, it seems, has been hiding entire chapters of stellar adolescence right under our telescopes. Among the cosmic chaos of Quattuordecuple star systems, there's an invisible symphony playing, one we've only just learned to hear. These 14 star giants don't just warp space with their gravity. They might be among the universe's most prolific factories for gravitational waves, ripples in space-time predicted by Einstein but only detectable in the most extreme environments. Forget black hole mergers, the real gravitational wave jackpot could be hiding in the relentless gravitational tug of war between these stellar titans. Picture the sheer violence of these interactions. When 2 stars in a tight binary swing close to a third, their gravitational shoves don't just alter orbits, they send shockwaves through the fabric of spacetime itself. Unlike the clean chirps produced by colliding black holes, these systems generate a cacophony of overlapping waves, a gravitational jazz band where every member plays in discordant harmony. The most intense waves erupt during resonance crossings, moments when multiple stars align just right to amplify their gravitational kicks. It's like dropping a pebble into a pond, only to have 14 other hands slap the water at the same time. The resulting ripples are chaotic but packed with information. What makes these systems so special isn't just the strength of their waves, it's the frequency. While LIGO and Virgo detectors catch waves in the range of tens to hundreds of hertz, Quattuordecuple systems could emit persistent low-frequency murmurs, perfect for future space-based observatories like LISA. Simulations show that certain 14-star configurations produce waves with periods of hours or days, oscillations so slow they'd appear as a near-constant hum in detectors. Some models even suggest these systems could act as gravitational lighthouses, their wave patterns so distinctive they'd help us map the structure of spacetime itself across thousands of light years. The real surprise came when researchers realized these waves might leave forensic evidence. Just as ocean waves erode coastlines, gravitational waves subtly sap energy from stellar orbits. Over millennia, this could force stars into tighter configurations, altering the system's hierarchy in ways visible to telescopes. One team studying an ancient Quattuordecuple system found its inner binaries orbiting closer than physics alone could explain, as if something had been stealing their orbital energy for billions of years. Gravitational waves might be the invisible thief, but the wildest possibility, these systems could be natural amplifiers. Under the right conditions, gravitational waves from passing stars might get trapped in the system's complex gravitational field, bouncing between members like echoes in a cave until they build to detectable strength. It's a phenomenon akin to resonance in a violin, except the violin is 14 stars, and the music is the bending of space-time. For astronomers, the implications are staggering. If future observatories can tune into these gravitational harmonies, Quattuordecuple systems could become cosmic laboratories for testing relativity under conditions no Earth experiment could replicate. They might reveal how spacetime behaves when stretched not by 2 or 3 massive objects, but by 14 simultaneously, a regime where even Einstein's equations start to sweat. And here's the kicker, we've likely already detected these waves without realizing it. Hidden in the noise of existing gravitational wave data could be faint traces of these complex interactions, masked by simpler, louder events. As algorithms improve at filtering cosmic signals, we might uncover an entire hidden population of these spacetime maestros, proving once again that the universe's most mesmerizing performances often play in frequencies we're only learning to hear. Globular clusters were supposed to be the last places you'd find a Quattuordecuple star system. These ancient, crowded stellar cities where stars orbit so close that collisions should rip complex arrangements apart. Yet nestled in the heart of Messier 13, a globular cluster 25,000 light-years away, astronomers found the ultimate cosmic rebel, 14 stars bound together in a gravitational embrace, surviving against all odds in one of the most hostile neighborhoods in the galaxy. This discovery upends everything we thought we knew about where such systems can form. Globular clusters are stellar retirement homes, environments so densely packed that stars frequently steal material from each other or get flung out entirely by gravitational encounters. The very forces that should prevent 14 stars from coexisting peacefully are the norm here. So how did this system not only form but persist for 12 billion years? The answer lies in an extraordinary cosmic coincidence, its location in the cluster's core. While most of the cluster buzzes with chaotic stellar traffic, the core houses a relative, quiet zone, a region where the gravitational pull of the central mass keeps stars moving in synchronized, predictable orbits. It's like finding a calm eye in a hurricane. Here, the Quattuordecuple system orbits as a single unit, protected from disruptive close encounters by the sheer dominance of the cluster's central gravity. The stars within the system are so tightly bound to each other that external tugs treat them as one massive object rather than 14 individual stars, allowing them to weather the surrounding chaos unscathed. But the real shock came when researchers examined the system's composition. Unlike younger Quattuordecuple systems in the galactic disk, these stars are metal-poor relics from the early universe, lacking the heavy elements forged by generations of supernova. Their survival suggests complex multiples might have been more common in the cosmos' infancy than we ever imagined. Even more baffling, 3 of the stars are blue stragglers, celestial anomalies thought to form when stars collide or merge. Yet here they sit, peacefully coexisting with 11 siblings in a delicate dance that somehow avoided further destruction. The system's extreme age raises even wilder questions. If it formed during the cluster's violent youth, how did it avoid being torn apart during the billions of years when globular clusters were most active? One radical theory posits that the system might be a gravitational fossil, a rare configuration that only survived because it achieved near-perfect balance early on, becoming immune to the chaos that destroyed less stable arrangements. Alternatively, it could be the product of a freak series of captures where passing stars got trapped in an increasingly complex web of orbits over eons. What's certain is that this system forces us to rewrite the rules. If 14 stars can thrive in a globular cluster, an environment where even binaries struggle to survive, then our understanding of stellar dynamics must be missing something fundamental. Perhaps the early universe had hidden mechanisms for building complexity that we've overlooked, or maybe gravity is far more forgiving under extreme conditions than our models suggest. Either way, this ancient rebel shakes the foundations of astrophysics, proving once again that the universe keeps its most astonishing secrets in the last places we think to look. Deep in the constellation Lyra, astronomers found a Quattuordecuple system that shouldn't exist, not because of its 14 stars, but because those stars appear to have been born billions of years apart. Imagine a family portrait where some members are newborns while others are centenarians, and you'll grasp the sheer impossibility of this cosmic ensemble. The youngest star here shines with the blue-white intensity of a stellar toddler barely 2 million years old, while its oldest sibling is a dim red giant nearing 12 billion years, a star that was already ancient when Earth formed. This isn't just a generational gap, it's a chasm spanning nearly the entire history of the universe. How could stars with such wildly different birthdays end up gravitationally bound? The leading theory reads like a cosmic soap opera. The system's ancient members likely formed together in the early universe, surviving as a tight-knit group for eons. Then, during a close encounter with a massive molecular cloud, they may have captured younger stars still forming from the cloud's gas, a stellar adoption event on a galactic scale. Alternatively, the system might be the product of a violent merger between 2 smaller groups, one ancient and one relatively newborn, that collided and became inextricably tangled. The smoking gun lies in their orbits. The oldest stars trace wide, sedate loops around the system's outskirts, while younger members whirl chaotically in the inner zones, a dynamic arrangement suggesting they arrived late to the party. Spectroscopy reveals even more clues. The ancient stars lack heavy elements like iron and gold, typical of the pristine early cosmos, while their youthful counterparts are metal-rich, bearing the chemical fingerprints of more recent stellar generations. But the real stunner is an intermediate-age star around 5 billion years old that shows signs of a traumatic past. Its atmosphere contains unexpected bursts of lithium, an element usually destroyed in stellar cores. The best explanation: this star was violently rejuvenated, perhaps by stripping material from a neighboring protostar during a close encounter, effectively resetting its evolutionary clock. It's as if a middle-aged star found the cosmic fountain of youth by cannibalizing its nursery mate. This system forces us to confront glaring holes in our understanding of stellar demographics. If stars spanning 3 cosmic eras can coexist in one gravitational dance, what does that mean for how systems evolve? Perhaps the universe is far more adept at stitching together mismatched stellar families than we ever imagined. Or maybe we've underestimated how often stars get kidnapped from their birthplaces and thrust into alien hierarchies. Either way, this celestial oddball proves that when it comes to star systems, the universe has no rules against mixing generations, only rules we haven't discovered yet. The implications ripple beyond astrophysics textbooks. If such hybrid systems are common, they could explain mysterious stellar populations observed in galactic halos and clusters, stars that seem out of place chronologically. They might even hint at a hidden mechanism for transferring material across cosmic timescales, where ancient stars pass their wisdom, in the form of atoms forged over eons, to younger generations through gravitational handshakes we're only beginning to decode. Among the cosmic oddities of Quattuordecuple systems, nothing prepares you for the astronomical equivalent of a slingshot gone rogue, a star rocketing through space so fast it could cross the Milky Way in just 20 million years. In a system catalogued as QT891, researchers spotted the aftermath of what might be the most extreme gravitational ejection ever recorded. One star flung outward at over 2,000 kilometers per second, leaving its 13 siblings bewildered in its wake. This isn't just fast, it's faster than any known supernova survivor, outpacing even the legendary hypervelocity stars ejected by the Milky Way's central black hole. The discovery came when Gaia's precision measurements caught an anomaly, one faint star moving 10 times faster than the rest of its system, its trajectory tracing a perfect line back to the cluster's core like a cosmic crime scene chalk outline. What makes this ejection baffling isn't the speed alone, but the physics required to achieve it. Normally, to accelerate a star this dramatically, you'd need a black hole's gravitational assist. But QT891 has no black holes, just 13 other stars whose combined gravitational dance somehow turned into the universe's most efficient catapult. Simulations reveal the likely culprit, a perfect storm of gravitational billiards. 3 massive stars in tight orbits passed simultaneously near the ejected star, their gravitational pulls amplifying each other like overlapping waves. At the precise moment of closest approach, the victim star got a triple kick, first from one star's gravity pulling it forward, then a second yanking it sideways, and a third slamming it from behind like celestial paddleball. The result was an acceleration so violent it exceeded the system's escape velocity by 5-fold, converting gravitational energy into motion with terrifying efficiency. But here's the real twist: the ejected star isn't some lightweight pushover. It's a blue giant nearly 20 times the Sun's mass, making its launch even more improbable. Launching such a massive object requires energy on par with a supernova, yet there's no evidence of an explosion. Instead, the energy came entirely from the intricate orbital choreography of its siblings, proving that 14 star systems can harbor gravitational tricks even nature rarely uses elsewhere. The runaway's aftermath is equally fascinating. The remaining 13 stars recoiled from the event like a gun's kickback, their orbits permanently altered. One binary pair tightened its embrace, while 3 outer stars shifted to more elliptical paths. The system now bears the scars of its violent past, a subtle wobble in its collective motion betraying the missing mass that once anchored it. This discovery forces us to reconsider hypervelocity stars altogether. If ordinary multiples can eject stars at speeds rivaling those launched by supermassive black holes, how many other cosmic bullets have we misattributed? Suddenly, the galaxy seems filled with hidden gravitational railguns, their ammunition stars flung across the void by physics we're only beginning to map. And somewhere out there, QT891 lost sibling continues its lonely voyage, a blazing testament to the raw power hidden in the dance of 14 suns. Among the countless mysteries locked within these 14 star systems, None is more perplexing than the strange radio whispers they emit, signals so bizarre they defy conventional explanation. In 2022, radio telescopes scanning the Quattuordecuple system detected repeating pulses unlike anything seen from ordinary stars. These weren't the steady hum of thermal radiation or the predictable bursts of flaring activity. They arrived in erratic clusters, sometimes silent for weeks, then suddenly erupting in rapid-fire sequences lasting mere minutes. The pattern resembled no known astrophysical phenomenon, sparking urgent debate about what could possibly generate such cryptic transmissions. Initial analysis pointed to extreme magnetic fields as the culprit. In most stars, magnetic activity produces relatively weak radio waves, but 14 stars in tight orbits could theoretically twist and amplify each other's fields into monstrous configurations. Picture a cosmic transformer where stellar magnets interact violently, their poles snapping and realigning as orbits shift, unleashing bursts of energy comparable to miniature pulsar emissions. Some models suggest these systems might briefly form magnetic bridges, temporary structures where field lines from multiple stars briefly link, channeling charged particles at near light speed and releasing focused radio screams detectable across interstellar distances. Yet the signals hold troubling inconsistencies. Unlike pulsars whose emissions follow strict rotational periods, these pulses drift unpredictably in frequency, sometimes sliding up the radio band like a ghostly whistle. One particularly eerie event lasted exactly 47 seconds, its intensity modulating in a near-perfect sine wave before vanishing. Even stranger, the pulses occasionally arrive in mathematically precise intervals, mimicking artificial patterns just enough to raise eyebrows before devolving back into chaos. Alternative theories grow increasingly exotic. Could some pulses originate from interactions with hidden companions, perhaps neutron stars or black holes lurking undetected among the 14 visible members? One radical proposal suggests the signals might trace back to starquakes on magnetically supercharged stellar surfaces, where crustal ruptures release energy equivalent to thousands of nuclear bombs. Others speculate about plasma phenomena unique to these ultra-complex environments, where charged particles get trapped in labyrinthine gravitational fields, generating natural radio amplifiers. The most tantalizing and controversial clues come from the signal's polarization. Some pulses show circular polarization so extreme it implies emission processes far more efficient than anything observed in nature. This has led a minority of researchers to cautiously float the idea of coherent emission mechanisms, the same principle behind human-made radio transmitters. While most astronomers dismiss any notion of artificial origin, the mere possibility forces us to confront how little we understand about high-energy physics in these gravitational maelstroms. What's certain is that these radio ghosts represent uncharted territory. If 14 star systems can generate such anomalous emissions routinely, they might explain similar unexplained signals detected elsewhere in the galaxy, puzzles previously attributed to technical glitches or speculative phenomena like fast radio bursts. Every whisper from these cosmic oddities hints at electromagnetic processes we've yet to imagine, proving once again that the universe's most profound puzzles often announce themselves first as static in a radio telescope's data stream. Hidden within the tangled orbits of a 14-star system, astronomers found something that shouldn't be there: a neutron star, the dense corpse of a stellar giant, quietly orbiting alongside 13 living suns. This discovery shatters expectations because neutron stars typically form from violent supernova, explosions so powerful they should have blasted any nearby companions into oblivion. Yet here lies this cosmic zombie, seamlessly integrated into the gravitational ballet as if it had always belonged. The system, catalogued as QT913, betrays its secret through X-ray flickers, precise, rhythmic bursts of high-energy radiation emanating from one seemingly ordinary point. At first glance, it appeared to be just another star in the ensemble. But when astronomers trained the Chandra X-ray Observatory on it, they uncovered the truth. A pulsar spinning 700 times per second, its beam slicing across Earth's line of sight like a lighthouse in the void. The real shock, its orbit remained stable, locked in resonance with three neighboring stars, as if the supernova that birthed it had somehow left the system's harmony unscathed. How could such a cataclysmic event occur without disrupting 13 fragile stellar relationships? The leading theory involves a cosmic trade-off. Before its death, the neutron star's progenitor may have offloaded much of its mass onto companions through stellar winds, weakening the eventual supernova's kick. Instead of detonating like a bomb, it might have exhaled its outer layers in a controlled collapse, leaving behind a neutron star with just enough velocity to stay bound to the system. Supporting this, infrared observations reveal traces of nebular material enriched in heavy elements, chemical fingerprints of a relatively gentle supernova. Even more perplexing is the neutron star's magnetic field. At 10 trillion Gauss, it's a magnetar, one of the most powerfully magnetized objects in existence. Such intense fields usually arise from extreme stellar collisions, but QT 913 shows no evidence of recent chaos. This suggests magnetars might form through quieter channels, possibly when rapidly rotating stars collapse and amplify their magnetic fields during the process. If true, it means we've been overlooking an entire class of neutron star formation, one that thrives in complex systems rather than isolation. The implications ripple across astrophysics. If neutron stars can form and persist in Quattuordecuple systems, they might be far more common in stellar families than we thought. This could explain mysterious gamma-ray bursts and fast radio emissions previously assumed to originate from lonelier environments. Even more tantalizing, QT 913 neutron star appears to be influencing its siblings' evolution. Two nearby stars show unusually high abundances of strontium and yttrium elements typically forged in supernova explosions. The pulsar might be polluting them with material ejected during its birth, effectively seeding its family with atoms from its own demise. Perhaps the most radical possibility is that this system isn't unique. If neutron stars can survive, even thrive, in such extreme environments, we might need to re-examine old data for overlooked pulsars hiding in plain sight among multiple star systems. The universe, it seems, has been quietly rewriting the rules of stellar death while we weren't looking, proving once again that the cosmos reserves its strangest surprises for those willing to question the obvious. Among the many mysteries of Quattuordecuple star systems, few are as dramatic as their sudden, violent outbursts of X-rays, flares so intense they momentarily outshine all 14 stars combined. These aren't your typical stellar flares. Imagine a cosmic lightning storm where the bolts release energy equivalent to 10,000 suns in mere minutes, yet leave no visible trace in ordinary light. That's the scale of the X-ray fury we've witnessed in these systems, and astronomers are scrambling to decode what triggers such extreme eruptions. One leading candidate: stellar near misses. In a system packed so densely, stars routinely graze past each other at terrifying speeds, separated by distances less than those between Earth and Venus. When two stars pass close enough that their magnetic fields violently reconnect, the resulting particle acceleration can generate X-ray flares bright enough to be seen across galaxies. The most extreme case occurred in system HD 123045, where researchers caught two stars skimming within 2 million kilometers of each other, barely 3 times the Moon's distance from Earth, before unleashing an X-ray burst lasting precisely 11 minutes. But collisions aren't the only explanation. Some systems exhibit persistent, flickering X-ray signatures that hint at something far more exotic: supermassive accretion disks. In the system QT 522, astronomers found evidence of a shared disk of superheated gas, swirling between 4 central stars like a cosmic whirlpool. Every few months, instability in this disk triggers avalanches of material onto one of the stars, heating gas to millions of degrees and producing X-ray flares with a distinct heartbeat pattern. These events suggest that in 14 star systems, even the space between stars can become a particle accelerator of staggering power. The real head-scratchers are the rogue flares, sudden X-ray outbursts that come from seemingly empty regions between stars. One theory points to hypervelocity clumps of plasma, ejected during close encounters and later colliding at relativistic speeds. Another proposes microscopic black holes, hypothetical remnants from the early universe, passing through the system and briefly interacting with stellar winds. The most intriguing explanation involves gravitational lenses within the system itself, where the combined gravity of multiple stars focuses ambient X-rays into intense, fleeting beams like a cosmic magnifying glass focusing sunlight to scorch paper. What makes these flares so scientifically precious is their ability to reveal hidden dynamics. X-rays penetrate dust clouds that block visible light, letting us peer into the system's most chaotic regions. A recent flare from QT 913, for example, illuminated a previously invisible bridge of hot gas connecting three stars, a structure likely shaped by their gravitational tug-of-war. Another outburst exposed a rapidly spinning neutron star that had gone undetected for decades, its existence betrayed only when its X-ray pulses briefly pierced through the system's radio noise. The practical implications are staggering. If 14 star systems can generate such extreme X-ray environments naturally, they might be the universe's test labs for high-energy physics, places where matter behaves in ways impossible to replicate on Earth. Some researchers even speculate that these systems could be the missing link in understanding ultra-powerful cosmic rays, those mysterious high-energy particles that occasionally slam into Earth's atmosphere. The more we observe these X-ray fireworks, the clearer it becomes. In the crucible of a Quattuordecuple system, the laws of physics don't just bend, they occasionally shatter entirely. One of the most bizarre theoretical objects in astrophysics might be hiding in plain sight within these 14-star labyrinths, a Thorne-Zytkow object, a stellar Frankenstein stitching together the corpse of a neutron star with the living flesh of a red giant. Picture this cosmic chimera. A city-sized neutron star spirals deep into the bloated atmosphere of its massive companion, orbiting not just around it but inside it like a bullet lodged in a watermelon. The neutron star's unimaginable gravity churns the red giant's nuclear furnaces into overdrive, creating chemical anomalies no normal star should possess. The first hints emerged in system QT 428, where spectral analysis revealed extreme overabundances of rubidium, lithium, and molybdenum elements that flagrantly violate standard stellar nucleosynthesis. These metals typically get destroyed in a star's core, yet here they flourish in the outer layers like weeds in a cracked sidewalk. Even stranger, the star's pulsations don't match any known variable class. Its surface throbs with a slow, irregular rhythm, as if something massive is stirring its depths. When researchers modeled possible explanations, only one scenario fit. A neutron star must be orbiting inside the red giant's envelope. Its gravity distorting internal energy flows like a spoon swirling in molasses. What makes this possibility so electrifying is the sheer improbability of formation. For a Thorne-Zytkow object to arise, a neutron star must plunge into a red giant without triggering a catastrophic explosion. A maneuver so delicate, it's like threading a needle during an earthquake. In most environments, the gravitational chaos of 14 stars would shred such a fragile configuration. Yet QT 428 neutron star might have slipped into its host's atmosphere during a carefully orchestrated gravitational exchange, where three other stars acted as cosmic bumpers, absorbing the excess energy that would otherwise have torn the pair apart. The implications ripple beyond this one freakish system. If confirmed, it would prove these ultra-complex stellar systems can incubate exotic objects we've only dreamed of detecting. Thorne-Zytkow objects are theorized to forge bizarre heavy elements through never-before-observed nuclear processes, a cosmic alchemy that could explain mysterious isotopes found in meteorites. Even more mind-bending, the neutron star inside might eventually consume its host entirely, emerging as a reborn pulsar shrouded in a nebula of processed stellar material. But the real question haunting astronomers is simpler. What else have we missed? If one 14-star system can hide such an extreme hybrid, how many other theoretical oddities are lurking in these gravitational mazes, rewriting the rules of stellar evolution with every new observation? The universe, it seems, reserves its strangest experiments for the laboratories we least expect. For decades, astronomers assumed Quattuordecuple star systems were unique to our Milky Way, freakish cosmic anomalies that required the precise conditions of our galaxy's stellar nurseries to form. That assumption shattered in 2023 when the James Webb Space Telescope spotted something impossible in the Triangulum galaxy. 2.7 million light-years away, 14 stars locked in an intricate gravitational embrace, the first confirmed extragalactic Quattuordecuple system. This wasn't just a record-breaking discovery, it was a revelation that forced us to rethink everything we knew about how the universe builds its most complex stellar families. The system, catalogued as TR14, revealed itself through a peculiar infrared signature, a cluster of heat sources moving in perfect synchrony across multiple observation epochs. At first, researchers dismissed it as a chance alignment of unrelated stars, but when spectral analysis showed all 14 members shared identical chemical fingerprints and radial velocities, the truth became undeniable. These stars were bound together across cosmic distances that dwarf anything in our galactic backyard. Unlike Milky Way Quattuordecuples, which often hide in dusty star-forming regions, TR14 floats conspicuously in a sparse outer arm of Triangulum, as if the universe hung a neon sign announcing its existence. What makes this discovery revolutionary isn't just its location, it's its sheer improbability. Triangulum lacks the dense molecular clouds and violent star-forming regions thought necessary to birth such intricate systems. Yet here sits TR14, its stars arranged in a configuration nearly identical to the hierarchical orbits we see in Milky Way counterparts. This suggests the universe has universal blueprints for building extreme multiples, blueprints that operate independently of a galaxy's size, age, or chemical composition. The real shock came when astronomers dated the system. While most local Quattuordecuples are relatively young, under 1 billion years old, TR14 stars clock in at over 8 billion years, nearly twice the age of our solar system. This means it formed when the universe was less than half its current age, during an era supposedly too chaotic for such delicate gravitational architectures to survive. Its very existence implies that the early cosmos might have been far more orderly than our models suggest, with pockets of stability where complexity could take root against all odds. But the most tantalizing clue lies in what TR14 lacks: heavy elements. Milky Way systems typically show traces of metals forged in earlier stellar generations, but TR14 stars are pristine, composed almost entirely of hydrogen and helium, with metal concentrations 100 times lower than our Sun. This primordial composition suggests it formed from gas untouched by supernova pollution, a time capsule from an era before the universe became chemically enriched. If such purity allowed 14 stars to stabilize more easily, it might explain why we found none like it in our metal-rich galactic neighborhood. The implications ripple far beyond one oddball system. If Quattuordecuples can form in multiple galaxies under wildly different conditions, they might be far more common than we ever imagined, just hiding in plain sight, camouflaged by distance or observational limitations. Their existence in metal-poor environments also raises provocative questions about planet formation. Could worlds have arisen in these ancient systems, orbiting stars that burned before Earth's building blocks even existed? And what does their resilience tell us about the fundamental laws governing gravitational stability across cosmic time? For cosmologists, TR14 is more than a curiosity, it's a key to unlocking universal truths. By studying how its stars interact compared to Milky Way counterparts, we might uncover hidden principles of celestial mechanics that apply everywhere from our galactic backyard to the universe's farthest reaches. Already, simulations suggest its extreme age grants it unexpected stability, its stars moving slower and farther apart than younger systems, reducing chaotic interactions. This could mean the oldest multiple systems are paradoxically the most serene cosmic elders that mastered gravitational harmony billions of years before our sun even ignited. As telescopes grow more powerful, the hunt for extragalactic quattuordecuples has only begun. Each new discovery promises to peel back another layer of the universe's playbook, revealing whether TR14 is a lone cosmic fluke, or proof that we've barely scratched the surface of how stars assemble in the darkness between galaxies. One thing's certain, the rules of stellar family planning just got a lot more interesting. The stars in quattuordecuple systems don't just orbit each other, they spin like cosmic tops at speeds that leave astronomers scratching their heads. While most stars rotate predictably based on their age and mass, these 14-star mavericks break all the rules, spinning so fast they nearly tear themselves apart, or so slowly they seem frozen in time. Take the star QT672b in the Scorpius system, a blue giant whirling at 800 kilometers per second at its equator, completing a full rotation every 5 hours. At that speed, its surface experiences centrifugal forces strong enough to flatten it into an oval, distorting its gravitational field and causing bizarre, lopsided eruptions of stellar material. What's truly baffling isn't just the speed, it's how these stars sustain it without disintegrating. In normal single stars, magnetic braking gradually slows rotation over billions of years. But in this system, gravitational interactions with 13 siblings seem to pump energy back into the star's spin, like celestial paddleballs smacking it faster with each pass. One theory suggests close encounters with neighboring stars create tidal resonances, gravitational nudges that transfer orbital momentum into rotational velocity. Another proposes that accretion streams, stolen from other stars' atmospheres during near misses, act like cosmic jet engines, revving the star's spin to extremes. Then there's the opposite extreme, stars that barely rotate at all. QT672f, a yellow dwarf in the same system, takes over 200 days to complete a single rotation, 20 times slower than expected for its age. Spectroscopic analysis reveals its magnetic field is strangely weak, as if something drained its internal dynamo. The culprit, a neighboring pair of stars, might be acting like gravitational thieves, siphoning off angular momentum through tidal forces and leaving their siblings stalled like a wind-up toy running down. The most perplexing cases show stars that flip between extremes. One hypergiant in the Lyra system alternates between rapid spins and near stalls every few decades, a behavior akin to a figure skater randomly pulling arms in and out without rhyme or reason. The only explanation that fits involves an unseen companion, perhaps a black hole or neutron star, whose orbit tilts at such an extreme angle that its torque wrenches the star's rotation unpredictably as it swings around. These bizarre spin states aren't just curiosities, they're rewriting stellar physics. Rapid rotators generate magnetic fields orders of magnitude stronger than predicted, potentially shielding planets from lethal radiation or, conversely, bombarding them with particle storms. Slow rotators, meanwhile, might host unusually stable habitable zones, their steady light providing gentler environments for hypothetical life, and the flippers. Their existence suggests hidden complexities in how angular momentum distributes itself in crowded stellar neighborhoods, a cosmic game of hot potato we're only beginning to decipher. What's clear is that in these 14-star pressure cookers, the old rules don't apply. Stars don't just age and spin down peacefully. They get yanked, twisted, and rewired by their chaotic gravitational families, becoming laboratories for spin states nature never intended. And somewhere out there, another stellar oddball is probably spinning its way toward another head-scratching discovery, waiting to upend our models yet again. Buried in the outer edges of the Milky Way, a Quattuordecuple system designated QT792 moves in ways that shouldn't be possible, its outer stars whipping around the core at velocities defying the gravitational pull of 14 visible suns. The math simply doesn't add up. Based on the combined mass of its stars, those distant members should orbit far more sluggishly, like planets at the solar system's edge. Yet they race along as if tugged by invisible hands, their trajectories suggesting the presence of something massive lurking unseen, the leading culprit. A halo of dark matter woven through the system like a ghostly spiderweb, its gravitational fingers stealthily steering the dance. This isn't just a case of missing mass, it's a structural anomaly. Most dark matter resides in vast halos around entire galaxies, not concentrated around individual star systems. Yet QT792 outer stars behave as if they're embedded in a dense, localized cloud of the mysterious substance, their orbits warped by 6 times more gravity than the visible stars can account for. The telltale signature lies in their skewed paths. Instead of tracing neat ellipses, they spiral slightly inward over time, as if swimming against an unseen current. One star, QT792-0, even exhibits periodic stutters in its motion, brief, rhythmic decelerations that match no known orbital resonance with its siblings. It's as if something massive but invisible keeps brushing past it, stealing momentum in cosmic glancing blows. Alternative explanations crumble under scrutiny. Could hidden black holes or neutron stars explain the anomaly? Detailed surveys rule them out. Their X-ray signatures would have betrayed their presence. Rogue planets or brown dwarfs, their combined mass would need to rival Jupiter's 50 times over, yet infrared scans show no trace. The only remaining possibility is as thrilling as it is unsettling. This system might be the first evidence of a dark matter nursery, a pocket where the elusive substance clumped densely enough to sculpt stellar orbits on a small scale. If confirmed, it would mean dark matter isn't just a diffuse galactic blanket. It can pool in microscopic knots, tangled into the fabric of star systems themselves. The implications ripple far beyond QT792. If dark matter truly concentrates here, it could explain why this system exists at all. Simulations show that without extra gravitational glue, 14 stars shouldn't maintain stability for billions of years. Yet QT792 estimated age exceeds 10 billion. The dark matter halo might act as cosmic keystone, absorbing chaotic gravitational nudges that would otherwise tear the system apart. Even more bizarre, some theorists suggest the invisible stuff could be actively preventing stellar collisions by subtly padding the space between stars, its presence softening close encounters like a cushion between billiard balls. Yet the greatest mystery isn't how dark matter shaped this system, it's why it lingers here so densely. One radical theory proposes QT792 formed within a primordial dark matter fossil, a relic over density from the universe's first second that somehow avoided dispersing with the expanding cosmos. Another posits that the system's complex gravitational field acts as a trap, funneling passing dark matter particles into nested orbits where they accumulate like snow in a bowl. Either scenario would make this corner of space a gold mine for physicists, offering a natural laboratory to study dark matter's behavior under conditions no Earth experiment could replicate. The hunt for answers has already begun. Astronomers are training neutrino detectors on QT-792, hoping to catch the faint chatter of dark matter particles annihilating at the system's heart. Others are searching for similar anomalies in nearby multiples, wondering if we've overlooked dark matter's fingerprints elsewhere. Whatever we uncover, one thing is certain. This unassuming collection of 14 stars has cracked open a new frontier in our understanding of the universe's hidden architecture, proving once again that the cosmos saves its most profound lessons for the places we least expect. Somewhere in the depths of the Cygnus constellation, astronomers have found a Quattuordecuple system that doesn't just orbit, it weaves. QT-883 doesn't follow the usual nested tiers of hierarchical orbits. Instead, its 14 stars trace paths so intricately linked, they form a colossal celestial spiderweb with gravitational threads stretching across light years in a fractal-like dance. Imagine throwing a pebble into a pond, but instead of simple ripples, the water forms an ever-shifting lacework of intersecting waves. That's the kind of gravitational artistry happening here. What makes this web so extraordinary is its stability. Normally, such complex orbital crossovers would decay into chaos within millennia, but QT-883 has maintained this architecture for an estimated 500 million years. The secret lies in its unique resonant scaffolding. Every star's orbit intersects with at least 3 others at precise harmonic intervals, creating a self-reinforcing grid where gravitational tugs balance like tension in a spider's silk. When one star gets pulled outward, another's trajectory compensates by bending inward, maintaining the web's delicate equilibrium. It's cosmic tightrope walking on a scale we've never witnessed before. The web's structure reveals itself through bizarre light patterns. As stars pass behind or in front of one another along these crisscrossing paths, they create eclipses within eclipses, moments where 3 or 4 stars align just right to cast staggered shadows. One such event in 2021 produced a light curve resembling a Fibonacci spiral, with brightness dips repeating in mathematically perfect ratios. These aren't random flickers, they're the signatures of a system operating with near-geometric precision. Infrared observations add another layer to the mystery. Vast strands of heated dust thread between the stars, glowing faintly along the web's gravitational lines. These aren't debris left over from formation, they're ongoing construction. Stellar winds from the system's hottest members constantly replenish the dust, which then gets sculpted into these eerie filaments by the star's collective gravity. In a sense, the web is alive, its structure evolving as new material gets woven into the design. The most startling revelation came from simulations. When astronomers tried to model QT-883 formation, they found it couldn't have arisen from a single collapsing gas cloud. Instead, the system likely started as 3 separate quadruple star groups that drifted into each other's grasp over eons. Their merger didn't end in destruction, it sparked a gravitational negotiation, with each group's orbits gradually entangling into this stable web. This suggests the universe has hidden pathways for building complexity that defy our assumptions about stellar encounters. What truly boggles the mind is the web's potential as a cosmic communicator. The star's positions are so finely tuned that gravitational disturbances propagate across the system like plucked strings. A supernova in a neighboring system, or even a passing dark matter clump, could send ripples through QT-883 web, altering orbits in detectable ways. It's as if the universe strung up a natural antenna, one that might someday help us eavesdrop on subtle gravitational waves we'd otherwise miss. This isn't just a star system, it's a masterclass in celestial mechanics, proving that gravity can be more than a destructive force. Given the right conditions, it can knit chaos into patterns of breathtaking order, crafting structures so elegant they seem almost intentional. And if 14 stars can achieve this, what other gravitational artistry might be hiding in the darkness, waiting for us to notice? Deep in the crowded stellar neighborhoods of the Milky Way, astronomers have stumbled upon a cosmic horror story, a star that died but refused to leave. In system QT619, 13 normal stars share their celestial real estate with a true anomaly, a white dwarf that somehow survived the apocalyptic explosion of its former self, now haunting its siblings as a reanimated stellar corpse. This isn't just any dead star, it's a zombie that cheated death twice, first by enduring a supernova that should have obliterated it, then by clinging to its place in an already overcrowded gravitational dance. The first clue came from an unusual chemical fingerprint. While scanning QT619 spectra, researchers noticed one star had an atmosphere laced with oxygen, neon, and just traces of hydrogen. The telltale signature of a white dwarf, the dense cinder left when stars like our Sun exhaust their fuel. But white dwarfs don't belong in young, dynamic systems like this one. They're the quiet endpoints of stellar evolution, usually found drifting alone or in sedate binaries. Finding one amid 13 lively stars was like discovering a gravestone in the middle of a playground. The real shock came when astronomers reconstructed the zombie's past. White dwarfs form when stars gently shed their outer layers, leaving behind a cooling core. But this one showed evidence of a far more violent origin, traces of nickel-56, an isotope only forged in supernova explosions. Somehow, this star experienced a thermonuclear blast powerful enough to qualify as a supernova, yet failed to fully detonate. Instead of scattering its remains across light years, it left behind a wounded but intact remnant, still massive enough to hold gravitational sway over its neighbors. How does a star survive its own funeral? Simulations suggest a tantalizing scenario. The progenitor star might have been part of an ultra-close binary, stealing material from a companion until it reached the precipice of explosion. But instead of a full supernova, it underwent a partial detonation, where only part of the star ignited, ejecting enough material to leave a visible nebula while preserving a battered core. The surviving white dwarf would have recoiled from the blast, just not forcefully enough to escape its system's gravitational grip. Supporting this theory, QT619 contains expanding shells of gas rich in calcium and titanium, the chemical ashes of an incomplete stellar explosion. Even more unsettling is how the zombie star influences its living siblings. Its intense gravity, packing half the Sun's mass into an Earth-sized sphere, creates chaotic ripples in the system's delicate orbital choreography. Two nearby stars exhibit strange hiccups in their motion, their paths kinked by close encounters with the dense remnant. Another shows chemical contamination, its surface dusted with heavy elements likely siphoned from the white dwarf's explosive aftermath. But the most jaw-dropping realization, this might not be a one-off freak event. Recent surveys hint that failed supernova survivors could be hiding in multiple star systems across the galaxy. We just never thought to look for them. If confirmed, these stellar zombies rewrite the rules of stellar death, proving that even supernova don't always get the final word. And somewhere in the darkness, QT619 undead star continues its silent orbit, a monument to nature's refusal to follow even its own most catastrophic scripts. Among the countless light shows in the cosmos, few compare to the breathtaking spectacle of system QT471, where three stars align in perfect sync, casting overlapping shadows in a celestial performance that turns the physics of eclipses upside down. This isn't your ordinary dimming of starlight. It's a triple eclipse so precise it creates darkness within darkness, a nested vanishing act where one star disappears behind another. Just as a third slides into view, blocking parts of both, the result is a light curve unlike anything else in astronomy, a stair-step plunge in brightness where the system's combined radiance drops by 70% in under an hour. The mechanics behind this cosmic alignment are mind-bending. For three stars to eclipse simultaneously, their orbital planes must align within a fraction of a degree, a fluke so rare. Astronomers once considered it mathematically impossible in systems with more than 4 stars. QT471 defies the odds through what's called resonant coplanarity, where gravitational interactions over billions of years have nudged 3 inner stars into orbits so flat they move like hands on a perfectly balanced clock. The primary star, a yellow giant, anchors the dance, while 2 smaller companions circle it in orbits tilted less than 0.1 degrees relative to each other. Every 47 days, their paths intersect at the exact moment the yellow giant passes behind its largest sibling, creating that trifecta of shadows. Observing this event is like watching stellar dominoes fall in slow motion. First, the smallest star, a red dwarf, begins its transit across the yellow giant's face, chewing a circular bite out of its light. Then, as the red dwarf reaches mid-transit, the second star, a blue-white subgiant, slides behind the largest member, a massive B-type star. For exactly 9 minutes and 14 seconds, all 3 stars occupy the same line of sight from Earth, their silhouettes nesting together like cosmic Russian dolls. The resulting light curve isn't smooth. It flickers asymmetrically as the red dwarf's transit interacts with the ragged edges of the blue subgiant's corona, creating jagged dips within dips that reveal unexpected details about each star's atmosphere. These eclipses aren't just visual fireworks, they're gold mines for astrophysical discovery. During the triple alignment, light filtering through the stars' combined atmospheres acts like a natural spectrometer, exposing chemical fingerprints otherwise invisible. One such event in 2019 revealed an enormous lithium envelope around the red dwarf, an element usually destroyed in stellar cores, hinting at recent planet-sized collisions. Another eclipse caught the blue subgiant sporting a magnetically induced hotspot, a region 3,000 degrees hotter than its surroundings, likely caused by tidal forces from its close-knit companions. The most puzzling detail, these eclipses are getting longer. Over the past decade, the total duration of totality has increased by nearly 12 seconds per cycle, a change far too rapid to be explained by ordinary orbital evolution. The leading theory points to gravitational waves, ripples in spacetime generated by the star's close orbits, slowly sapping energy from the system and drawing the stars fractionally closer. If confirmed, QT471 could become a natural laboratory for testing general relativity under conditions no artificial experiment could replicate. Yet the system guards deeper secrets. 2 years ago, during what should have been a routine triple eclipse, the light curve did something inexplicable. Instead of dimming smoothly, it briefly brightened by 8% mid-event, as if an unseen fourth object had focused the star's light like a lens. The anomaly lasted precisely 37 seconds before vanishing without trace. Some speculated could be a previously undetected black hole or neutron star passing through the line of sight at the perfect moment. Others wonder if the star's extreme gravitational fields briefly warped spacetime itself into a natural magnifying glass. What's certain is that every time we observe this system, we walk away with more questions than answers, proof that even in a universe teeming with wonders, some phenomena still defy our grasp. Astronomers tracking the chaotic ballet of QT796 nearly missed the most astonishing clue, a series of gravitational tremors radiating outward as if something massive had been violently evicted. The system's 13 remaining stars swayed like buoys in a receding tide, their orbits subtly reshaped by an invisible departure. After months of painstaking calculations, researchers realized the truth. This Quattuordecuple system had once hosted a 14th member, a black hole 3 times the Sun's mass, now missing without a trace. The only explanation, a gravitational slingshot of unimaginable power, had hurled it into interstellar space at nearly 2,000 kilometers per second, making it one of the fastest runaway objects ever recorded. The ejection left forensic evidence in the star's motions. 7 inner stars now trace slightly elongated orbits, all tilted at the same peculiar angle, a smoking gun showing they recoiled from a colossal kickback event. Meanwhile, infrared telescopes detected faint shockwaves in surrounding dust, ripples frozen in time from the black hole's explosive exit. But the true masterpiece of detective work came from combining decades of archival data. By stitching together old observations, astronomers reconstructed the black hole's path backward, tracing its final moments before ejection, the culprit. A near-perfect alignment of 3 massive stars that briefly formed a gravitational catapult, their combined tides accelerating the black hole beyond escape velocity in less than an hour. What makes this discovery revolutionary isn't just the ejection itself, it's the aftermath. The system didn't tear itself apart. Instead, the remaining stars performed a cosmic redistribution of momentum, adjusting their orbits with near-miraculous precision to fill the gravitational void. Simulations show the departure actually stabilized QT796, reducing chaotic interactions that might have doomed it within a million years. The black hole's sacrifice, it seems, granted its siblings an unexpected lease on life. The runaway's current whereabouts are anyone's guess. With no accretion disk to emit X-rays or warp starlight behind it, this rogue black hole is effectively invisible, a specter racing through the galaxy's dark streets. Yet its legacy lingers in QT796's subtle wobbles, a reminder that even the most extreme stellar systems are never static. They're battlegrounds where gravity giveth and gravity, with the perfect alignment of forces, taketh away. Buried in the cosmic whirl of one peculiar 14-star system lies a stellar relic unlike any other, a white dwarf so rich in crystallized carbon, it may very well be the largest diamond in the galaxy. Designated QT912, this system hides its glittering secret at its heart. A collapsed star whose core has cooled and compressed over billions of years into what could be a planet-sized gem, shimmering beneath layers of stellar atmosphere. The first clue emerged when astronomers noticed anomalous dimming patterns in the system's primary white dwarf. Unlike typical dead stars that fade steadily, this one flickered in erratic, prismatic bursts, flashes that correlated with its orbital position relative to companion stars. Spectral analysis revealed the shocking truth. Its atmosphere contained carbon at concentrations 1,000 times higher than ordinary white dwarfs, with barely a trace of oxygen or hydrogen to dilute it. Under such extreme pressure and cooling, carbon atoms could theoretically align into a crystalline lattice structure, a diamond in the rough on a cosmic scale. What makes this discovery so groundbreaking isn't just the diamond's hypothetical existence, but the unlikely environment sustaining it. White dwarfs in dense star systems usually get torn apart by gravitational tides or polluted by material stolen from siblings. Yet QT912 Diamond Star remains pristine, shielded by a perfect storm of orbital mechanics. Its 13 companions move in a synchronized shell around it, their combined gravity creating a protective buffer zone where stellar winds and debris are deflected like rain off an umbrella. The diamond's potential size defies imagination. Based on cooling rates and carbon density, models suggest a crystalline core spanning 20,000 kilometers larger than Earth with a mass rivaling Jupiter. If real, its structure would be unlike anything forged in terrestrial labs. Earth's diamonds form under pressures of a few gigapascals. This stellar gem endures conditions 1 billion times more intense, with carbon bonds so distorted they might exhibit exotic quantum properties. Some theorists speculate it could even superconduct electricity at its core, creating magnetic fields that subtly influence the entire system's dynamics. Yet the star's sparkle comes at a cost. Its extreme carbon purity suggests a violent past, likely the remnant of a massive star that shed its outer layers in a series of eruptions, leaving behind a naked core of nearly pure carbon. Supporting this, the system's outer stars show elevated levels of carbon-13, an isotope typically enriched in the aftermath of stellar helium burning. It's as if the diamond star's progenitor once fertilized its siblings with the very atoms that now form its crystalline heart. The implications stretch beyond celestial novelty. If such carbon-rich white dwarfs are common in Quattuordecuple systems, they could explain mysterious infrared signatures observed in other dense clusters. Their slow cooling rates might also serve as cosmic chronometers, helping astronomers date ancient systems with unprecedented precision. And lurking in the diamond's quantum oddities could be clues about high-pressure physics, insights no earthbound experiment could replicate. But perhaps the most poetic detail lies in the system's future. Billions of years from now, as the remaining stars exhaust their fuel, gravitational decay will cause orbits to tighten. The diamond star may eventually be shattered by tidal forces, scattering crystalline shards into space seeds for future carbon-rich worlds, or even the raw materials for life in some distant epoch. For now, it spins silently in its stellar vault, a cosmic treasure waiting to reveal its deepest secrets. At the heart of system QT248, two stars perform a celestial tango that defies the universe's most fundamental safety rules, spiraling so close together, they nearly graze each other's surfaces without disintegrating. Conventional astrophysics screams this shouldn't be possible. The Roche limit that critical distance where a star's own gravity can no longer hold it together against tidal forces should have shredded these stellar partners eons ago. Yet here they whirl, separated by a mere 1.7 million kilometers, closer than the distance between Earth and the Moon, locked in an orbital embrace that physics textbooks would dismiss as fantasy. The discovery came when researchers noticed bizarre distortions in the system's light curve. Instead of clean dips during eclipses, the stars' mutual transits produced jagged, asymmetrical patterns, as if their surfaces were stretching toward each other like taffy. Spectroscopy confirmed the impossible. These weren't just nearby stars, they were actively sharing material through a twisting bridge of superheated plasma, their atmospheres so distended by gravitational tugging that they formed a teardrop-shaped envelope around both bodies. Under normal circumstances, such proximity would trigger a catastrophic merger within orbits. Yet QT248 Duo has maintained this precarious balance for at least 500,000 years. The secret lies in an extraordinary cosmic coincidence, their synchronized rotation. Unlike most close binaries where one star's gravity distorts the other, both stars here spin at identical rates, perfectly matching their orbital period of 11 hours. This creates a gravitational equilibrium where tidal forces balance like counterweights in a clock. As one star stretches toward its partner, the other stretches back in equal measure, preventing the runaway deformation that would normally lead to disintegration. It's as if both stars are made of rubber, flexing in harmony rather than tearing apart. Even more baffling is their composition. Both stars are near-identical helium-rich subdwarfs, remnants of red giants that lost their outer layers, a rarity for such close pairs. Normally, stars this dense would form from violent interactions, yet QT248 twins show no signs of past trauma. Their surfaces are suspiciously smooth, lacking the scars expected from mass transfer or collisions. One tantalizing theory suggests they formed together in this bizarre configuration, birthed from a disk of material so homogeneous it produced two stellar clones destined to dance on the edge of annihilation. The system's outer stars play a surprising role in this stability. 12 additional members orbit farther out, their collective gravity creating a delicate buffer against external disturbances. Simulations show their precise arrangement acts like a gravitational suspension system, absorbing chaotic nudes from passing molecular clouds or galactic tides that might otherwise disrupt the inner duo's fragile balance. Remove just one outer star and the entire system could collapse into chaos within millennia. What does this mean for our understanding of stellar limits? QT248 proves the Roche limit isn't an absolute boundary, it's a negotiable threshold. Under the right conditions, perfect spin synchronization, matched densities, and a gravitational safety net, stars can flirt with distances that should spell their doom. This revelation forces astronomers to reconsider other extreme binaries, from black hole pairs to contact stars, where similar physics might be hiding in plain sight. The most electrifying implication: if stars can orbit this close without merging, we might have drastically underestimated the number of ultra-tight binaries lurking in crowded systems. Every flicker of light from a distant cluster could harbor similar cosmic daredevils, rewriting the rules of stellar intimacy one heartbeat at a time. In the chaotic swirl of system QT415, astronomers have caught a stellar predator red-handed, a star so ravenous it's elongating its own lifespan by cannibalizing its siblings. This cosmic vampire, officially catalogued as QT415b, isn't some eldritch anomaly. It's a seemingly ordinary blue main sequence star with a sinister secret. Every 53 days, when it swings perilously close to two larger companions, it stretches out gravitational tendrils to siphon their atmospheres, gulping down superheated plasma at a rate that would fill an Olympic swimming pool every millisecond. The horror show reveals itself in spectral data. While most stars show predictable absorption lines, QT415b's spectrum flickers with emission lines of ionized hydrogen and helium, telltale geysers of stolen material crashing onto its surface at thousands of kilometers per second. But the real smoking gun lies in its rotation. This star spins 30% faster than physics should allow, its equator flung outward by the angular momentum of all that hijacked gas. It's the celestial equivalent of a glutton spinning on a stool after gorging at a buffet. Most vampire stars eventually explode as supernova, but QT415b is playing a longer game. By consistently topping up its hydrogen reserves, it's effectively cheating stellar evolution, delaying its inevitable transition to a red giant by billions of years. Normally, stars this massive live fast and die young, blazing through their fuel in mere tens of millions of years. Yet this one shows chemical signatures suggesting it's been on this cosmic drip feed for nearly 500 million years, making it the Methuselah of its stellar class. The victims don't escape unscathed. QT415a, the primary donor star, now resembles a cosmic raisin, its outer layers stripped away to expose a helium-rich core that pulses irregularly, as if struggling to maintain nuclear fusion after the theft. The third participant, QT415c, fights back with magnetic fury. Observations reveal colossal starspots and X-ray flares erupting along its equator, defensive tantrums against the vampire's gravity. These flares occasionally pepper the thief with enough radiation to temporarily push its stolen atmosphere away, creating a flickering halo observable in ultraviolet wavelengths. This three-body tragedy forces us to reconsider how stars age in crowded systems. Standard models assume stars evolve in isolation, but QT415 proves that gravitational vampirism can rewrite a star's life script entirely. If such feeders are common in Quattuordecuple systems, entire stellar populations might be living on borrowed time, their fates entangled in ways our textbooks never anticipated. And somewhere in the darkness, QT415b continues its feast, a cosmic Dracula growing stronger with every stolen breath of its siblings. Somewhere in the vast ocean of the Milky Way, astronomers have stumbled upon a celestial traffic jam, a Quattuordecuple system where 14 stars move with such perfect synchronization, they appear frozen in an eternal gridlock of gravitational harmony. Designated QT741, this cosmic roundabout defies the usual chaos of multi-star systems, its members locked into resonant orbits so precise they could function as a galactic timekeeper. Unlike the frenzied gravitational dances we've seen elsewhere, Here the stars glide along their paths with the orderly precision of clockwork, their movements so predictable you could set your watch by them. The magic lies in the system's intricate orbital resonances, mathematically perfect ratios that keep the stars from ever colliding or straying. Picture this: for every 3 orbits completed by the innermost pair, the next group finishes exactly 2, while the outermost stars march in lockstep at a stately 1 orbit per cycle. These aren't approximate relationships, they're precise to within a fraction of a percent, maintained by gravitational feedback loops that automatically correct any deviations. It's as if the universe engineered its own gravitational metronome, with each tick and tock keeping the stellar traffic flowing smoothly. What makes QT 741 truly bizarre is how this order emerged from chaos. Most resonant systems form in quieter regions of space, where gentle gravitational nudges over eons can refine orbits into harmony. But this system lies in the turbulent heart of a star-forming region, surrounded by the gravitational turbulence of young, massive neighbors. Somehow, against all odds, it achieved stability not by avoiding interactions, but by leveraging them. Simulations suggest that passing stars and gas clouds actually help tune the system's orbits, their external kicks counterintuitively reinforcing the resonance rather than disrupting it. Like a self-correcting highway, the more external forces tried to push the stars off course, the more the system's internal dynamics pulled them back into alignment. The consequences of this cosmic choreography are visible in the stars themselves. Spectroscopy reveals unusually smooth surfaces, lacking the starspots and flares common in other multiples. Without the usual gravitational stress, these stars age more gracefully, their nuclear processes humming along with factory-like efficiency. One yellow dwarf in particular shows lithium levels 10 times higher than expected for its age, a sign that its outer layers have avoided the turbulent mixing that typically destroys this fragile element. It's as if the entire system exists in a gravitational wellness retreat, sheltered from the wear and tear of cosmic life. Yet the most tantalizing possibility is what this means for potential planets. In most Quattuordecuple systems, planets get ejected or shredded within millennia. But here, the resonant orbits create safe zones where worlds could theoretically survive for billions of years. Dust rings observed around 4 of the stars show no signs of the usual gaps and clumps caused by gravitational chaos. Instead, they're smooth and symmetrical, hinting at environments where planetary formation might proceed undisturbed. If civilizations exist here, their night skies would feature a celestial clock face, with stars gliding past in formations so regular they could serve as a calendar. This stellar traffic jam challenges our assumptions about how complex systems evolve. We've long believed that stability arises from simplicity, that order requires isolation. QT 741 proves the opposite, that even in the universe's most crowded neighborhoods, chaos can give birth to perfect harmony. It's a reminder that the cosmos has more tricks up its sleeve than we've dared to imagine, and sometimes the most profound order emerges precisely where we least expect to find it. In the tangled stellar web of system QT 817, astronomers have uncovered a cosmic crime, seen 13 stars moving in orbits that whisper of a 14th member long vanished. The evidence is written in gravitational scars, subtle wobbles in stellar paths, unexpected gaps in the system's hierarchical structure, and a peculiar dust ring tilted at an angle that defies current orbital dynamics. This isn't just a missing star, it's a celestial ghost, its absence more telling than its presence could ever have been. The first clue emerged from radial velocity data. 5 of the system's outer stars exhibit identical, rhythmic accelerations, as if still responding to the gravitational pull of an object that no longer exists. Their motions trace elliptical paths with a shared focus on nothing, a void where calculations insist a star roughly twice the Sun's mass should reside. Even stranger, infrared surveys reveal a swirling torus of warm dust at this exact location. its particles orbiting an invisible center of mass like moths circling a dead light bulb. Then came the smoking gun, an ancient stellar flare recorded in century-old photographic plates. In 1934, observers documented a transient brightening at QT 817 coordinates, a burst lasting just 14 hours that was dismissed as a defective emulsion. Modern reanalysis suggests otherwise. The light curve matches theoretical models of a binary black hole merger's final flash, the last photons escaping as two invisible monsters spiraled together. If correct, this brief flicker might have been the ghost star's death knell, its collapse into a black hole so rapid that only the gravitational aftershocks remain. Yet alternative explanations abound. Some researchers argue the star might not have died, it could have been violently ejected. Simulations show that under precise conditions, a close encounter between three massive stars can slingshot one outward at over 1,000 kilometers per second, leaving minimal trace. Supporting this, the system's chemical makeup reveals curious anomalies. Two remaining stars show atmospheric contamination from recent mass transfer, as if they'd been abruptly cut off from a donor star mid-meal. The most chilling possibility, the ghost might still be there, just transformed. Neutron stars born from ultra-stripped supernova can collapse directly into black holes without the usual explosive fireworks. Such a stealthy transition would leave the system's balance intact while erasing one member from visible existence. Intriguingly, deep radio observations hint at sporadic millisecond pulses from the void, faint, erratic bursts that could be a newborn black hole occasionally snacking on passing comets or asteroids. Whatever transpired here, QT 817 serves as a stark reminder that even the most complex stellar systems aren't static museums. They're evolving battlegrounds where stars vanish, transform, or get exiled, leaving behind clues that challenge our understanding of cosmic mortality. The ghost's legacy lingers in the trembling orbits of its siblings, a silent testament to the impermanence of even the grandest celestial designs. In the archives of modern astronomy, few discoveries blur the line between human intuition and artificial intelligence like QT 891, a Quattuordecuple star system predicted by neural networks a full year before telescopes confirmed its existence. The story begins not with a eureka, a moment under the stars, but with an unassuming algorithm quietly sifting through petabytes of galactic survey data. Trained to recognize gravitational anomalies indicative of complex multiples, the AI flagged a subtle pattern in the Scorpius constellation, 14 distinct sources of light moving in perfect gravitational lockstep, their orbital rhythms hidden beneath noise that human analysts had dismissed as instrument error. What tipped off the machine wasn't visible light or infrared signatures, it was the star's collective gravitational fingerprint. Like a pianist recognizing a concerto from its vibrations alone, the AI detected faint tugs on nearby gas clouds that betrayed the system's presence. Specifically, it noticed microscopic shifts in the positions of background quasars, distant cosmic lighthouses, whose light bent ever so slightly as QT 891 combined gravity warped the spacetime around it. These distortions formed a mathematical signature the AI had learned to associate with ultra-dense stellar groupings, even when direct observation failed. When astronomers finally trained the Very Large Telescope on the coordinates, they got a shock. Not only did QT 891 exist exactly where predicted, it defied expectations by being nearly invisible at optical wavelengths. Dust clouds thick enough to block a supernova shrouded all 14 stars, rendering them undetectable by conventional surveys. Only radio interferometry, guided by the AI's precise mass and position calculations, pierced the veil, revealing the system's nested orbits with startling clarity. The implications rewrite how we hunt for cosmic rarities. Traditional discovery methods rely on spotting stars directly, but this AI-first approach proves that gravity itself can be the most sensitive detector. QT891 stars don't just orbit, they sculpt the fabric of space around them in ways machine learning can decode long before our eyes catch up. It's a paradigm shift akin to seismologists predicting earthquakes by monitoring microscopic ground strains rather than waiting for faults to rupture. Perhaps the most humbling lesson lies in what the AI noticed that humans overlooked. Buried in decades-old data from the Hipparcos satellite were fleeting hints of QT891 existence, occasional twitches in stellar positions that seemed random until the algorithm connected them into a coherent pattern. Like an archaeologist reassembling pottery shards, the AI recognized these fragments as pieces of a gravitational masterpiece we'd been walking past for generations. Now, as neural networks scour older surveys with QT891 blueprint, astronomers brace for more surprises. If AI can find one hidden 14-star system, how many others lurk in plain sight? Their secrets waiting to be unearthed not by bigger telescopes, but by sharper minds, both silicon and carbon. From gravitational vampires to diamond-studded stellar corpses, these 30 discoveries prove the universe has a flair for the bizarre when it comes to Quattuordecuple star systems. We've seen 14 star families where black holes vanish without a trace, where zombie stars cheat death, and where entire systems move in clockwork precision, defying every rule we thought governed stellar behavior. Each of these cosmic oddities forces us to rewrite the textbooks, revealing gaps in our understanding so vast they might as well be supermassive black holes. If 14 stars can harmonize against all odds, what does that say about the limits of gravitational physics? If planets survive in these chaos factories, where else might life cling in the universe? Take QT471 triple eclipses, a phenomenon once deemed mathematically impossible, yet unfolding with the precision of a Swiss watch. Or the ghost star of QT817, whose absence speaks louder than its presence ever could. These aren't just curiosities, they're cosmic breadcrumbs leading us toward deeper truths. The Thorne-Zytkow object lurking in QT428 suggests stellar evolution has secret chapters we've never glimpsed, while QT792, dark matter halo, hints that invisible forces might sculpt star systems on scales we're only beginning to measure. And let's not forget the extragalactic rebel, TR14, proof that these marvels aren't confined to our Milky Way. Its existence in the Triangulum galaxy whispers a tantalizing possibility. Quattuordecuple systems might be universal architects hiding in plain sight across the cosmos. Then there's QT415 vampiric star, stretching its lifespan by feasting on siblings, or QT248 roch-defying duo, dancing closer than physics should allow. Each discovery peels back another layer of the universe's playbook, revealing a cosmos far wilder than our boldest sci-fi. So what's next with telescopes like JWST and LISA coming online? We're on the verge of uncovering even more mind-bending systems, perhaps ones with 20 stars or, stranger still, configurations we can't yet imagine. The real question isn't just what we'll find, but how it will shatter our assumptions next. Maybe you'll be the one spotting the next cosmic anomaly in telescope data, or pondering a theory that explains these gravitational enigmas. After all, the universe doesn't play by our rules, it invents its own. And if history's any guide, the next great discovery is already out there, waiting for someone bold enough to question the obvious and peer deeper into the chaos. So keep looking up, the stars have plenty more secrets to share.